We're going to look at serial dictatorships in the presence of coalition formation. What this means is after each agent submits a ranked list, agents have the opportunity to partition themselves into coalitions. What this means is that a group of agents get together and decide that they're going to go into the dictatorship all together. In the second step, when each agent is assigned a random number, what happens now is first, one of the N agents is picked to be the dictator. The dictator's coalition, in a uniform random ordering, gets to go first. Then after that, the rest of the agents in a uniform random ordering go. What this means is if any agent in our coalition benefits, becomes the dictator, then we all benefit. But if an agent not in our coalition becomes the dictator, then we all lose together. The third step is going to work exactly the same, where each agent is just assigned to their top remaining choice when it's their turn in the ordering. More formally, a coalition is just a subset of the agents, and a coalition structure is a partitioning of the agents into coalitions, where each agent belongs to exactly one coalition. Keep in mind that an agent who doesn't want to join any coalitions can belong to a coalition consisting of just herself, and that still counts as a coalition.
A coalition formation game is a mechanism that takes the set of agents, the ranked list of their preferences, and returns a partition or coalition structure of the agents. We have done a theoretical analysis of a number of instances of such games, including examining dominant strategies when they exist, equilibria and stability, truthfulness, and more generally, optimal behavior of selfish agents.
The first model we consider is where agents have zero knowledge of other agents' preferences. In this model, each agent can only try to minimize her expected spot in the order because she has no other information to optimize over. This is also equivalent to all agents having the same preference list, up to a couple caveats. And we do this because it's very difficult to reason about these formation games in the presence of preferences. And this is because one agent's actions can have very far-reaching consequences in terms of what resources are available at some point later in the mechanism. We also may suspect, some of us, that general analysis may be actually theoretically intractable. For example, maybe it's computationally difficult for an agent to determine what the optimal coalition for them to be in is, or something along those lines.
As Ben mentioned, the model where each agent has zero knowledge of all other agents' preferences can be modeled with all people having the same preferences. We motivate this example by considering something like people standing in line to buy tickets, where everyone's preferences are the same, everyone wants a better ticket, but not everyone has to stand in line at the same time to get a ticket. People can join in groups to buy tickets and then randomly distribute the tickets among the members of their group.
Seems fine. The first game that we analyze is what we call the free coalition formation game. In this game, no one can prevent anyone from joining their coalition, so each agent can join whatever coalition they want. We model this as a one-shot game where each agent just chooses an integer from 1 to n inclusive. Each coalition is a set of agents that chose the same integer, and we ignore integers that no one chose. We reason about, suppose you knew what coalition everyone else was choosing, which coalition would you want to switch to? And through this reasoning, we come up with dominant strategies that imply a dominant strategy equilibrium. We now present our results on optimal behavior for selfish agents in the free coalition formation game. On a high level, there's a fundamental trade-off in terms of coalition size, in that the larger the size of your coalition, the more likely it is that the dictator will be a member of your coalition, and so that your coalition gets to go first. On the other hand, the larger your coalition is, the less exclusive it becomes, and so the benefit you get from your coalition going first is smaller. For example, if you're in a coalition all by yourself, the probability that your coalition is chosen is very low. But if your coalition is chosen, you guarantee that you will be able to go first. It turns out that the benefit of being in a smaller coalition of exclusivity is far outweighed by the benefit of being in a larger coalition, that your coalition is more likely to get to go first. We show this formally in our report through a lemma and two theorems. In lemma 1, we say that if C1 and C2 are any two coalitions, where C2 is at least as large as C1, then any agent in C1 can strictly increase her utility by switching to C2. And C2 will be larger after she switches. We use this to show theorem 1, and it's not too hard to see how, which says that belonging to the largest coalition is a dominant strategy. And the reason for this is that if I'm not in the largest coalition, then lemma 1 more or less implies that I should always switch to the largest coalition. Then theorem 2 says that all agents choosing the same coalition is a unique dominant strategy equilibrium. And the reason for this is that if there's more than one coalition, then one of them must be larger than the other one. And so we can apply lemma 1 to show that all of the agents in the smaller coalition must switch to the larger one, and once you iterate this process, eventually all of the agents have switched to the larger coalition, and only one coalition remains.
Math!
We now consider the exclusive coalition formation game, where we allow agents to prevent agents from joining their coalition if it would not benefit them. The idea for this is that if all agents are in the same coalition, this is the same as all agents being in separate coalitions, since the game has a fixed sum utility. Therefore, we hypothesize that there is some coalition size in the middle, where adding too many more agents will decrease the benefit you get, but again, if you don't have enough agents, it won't be as good because your coalition is less likely to be chosen. We show this formally with a lemma and a theorem. The lemma says that if an agent in C1 requests to join C2, C2 will accept if and only if the difference in their sizes is smaller than n over 2. We use this to show theorem 3, which says, assuming agents do not derp, where derp is formally defined in our report, the exclusive coalition formation game always terminates with exactly two coalitions, one with size exactly 3n over 4. The reason for this is that if I'm in a coalition of size 3n over 4, I won't accept any more agents unless they come from a coalition with size larger than n over 4. But since there are only n total agents, this is impossible. If there are many small coalitions, it will be in all of their best interest to merge into a larger coalition up to n over 4.
Cool. So we also want to analyze this model when we have preferences, but unfortunately math is hard, much like life. So we chose specific narrower models in which to analyze. So as an example to motivate this model, say that you had a room full of toddlers and a box of toys. If any of those toddlers don't get their first choice of toy, they're going to throw a tantrum and have zero utility. So correspondingly in this model, instead of submitting a full preference ranking, each agent submits only their top choice, and then during assignment, if their top choice isn't available, they get nothing, and they have zero utility. And otherwise, the model is exactly the same as our original one. If we assume that agents are constrained to pick the top choice that they submitted, then this mechanism is truthful. And we see that agents will want to maximize the ratio of the size of the coalition they're in to the number of competitors, which means the number of people in that coalition sharing their top choice, modulo some caveats that aren't really important. And based on this result, it's hard to characterize exactly what the equilibria in this model are, but we can say that they obey something called top choice profile containment. So what that means, in this example, for instance, if we arrange the coalitions by size, then each coalition, the top choices are contained in the top choices of the next one, and so on all the way up the chain. Alternatively, here is a non-example of that because neither of these two coalitions contain the top choice profile of the other. And as a result of that, for instance, if A switched from this coalition to this coalition, then A would be, if one of the A's switched, then they would be in a strictly larger coalition with the same number of competitors. So as we saw, they would prefer to be in that coalition. Therefore, this is not stable because it doesn't obey top choice profile containment. On the other hand, if the model is not truthful, as in if the agents can lie about what their top choice is and then pick something other than what they said, this isn't truthful because it might be advantageous to lie about what your top choice is so you can get in a bigger coalition because you pretend that you aren't competitors with the people you're actually competing with.